So hi everyone, welcome to the AATRN seminar. The speaker today is Justin Curry, and he's going to teach us about exemplars of sheaf theory and TDA.
Thank you for the introduction, Sarah, and thank you to the organizers for inviting me. The AATRN seminar has had such a great footprint and such a good format for our community. It's an honor to be able to give my talk to you all now. I've tried to be mindful and sort of truncating this talk so it fits within 40 minutes, but I want to first thank my my sponsors for supporting my research and most importantly, supporting my students. The theme of today is we're going to talk about my favorite thing, which is sheaf theory and its dual cousin, cosheaves theory. And I'm going to try to convince you that it integrates extremely well into topological data analysis. And in fact, ideas from TDA have been pouring back in through sheaf theory and cosheaves theory, which offers all these traditional fields like algebraic geometry and algebraic topology, sort of new tools and new perspectives, because we're actually integrating with things like noise and sort of sampling ideas, which are more pertinent in the implied realm. Broadly, this talk's going to have 4 chapters, but broken into 2 parts. The first part is going to be focusing on how we can use sheaf theory to model individual instances of things from TDA, one being persistent homology and another being this new tool, which I want to advertise, called decorated merge trees. And then the second half of the talk, I want to kind of show how the sheaf theory perspective can be used to study the space of all data sets and also the space of all these topological summary objects like merge trees or barcodes. So of course, I'd be remiss if I didn't show the typical picture of persistence, which is, we'd start with a data set. We can think of this as a point cloud, but persistence takes the perspective that this isn't standing in isolation, but rather is part of a 1-parameter family of spaces, where you can see sort of topological features come and go. And the kind of mantra that traditional persistence uses is that this family of spaces that data sets fit into usually are ordered in one way or another. There's usually a closer range and a larger range, or there's sort of a denser regime or a sparser regime. And you want to understand how things like homology vary as you move from one parameter value to the next. But I'm of the belief that this actually misses out on the real power of TDA, which is that we have now new tools for understanding the topology of level sets of a map when we're mapping to a metric space. And so for me, really what TDA does is it sort of algebratizes the fiber, that's the inverse image of a point, via either pi0, turning it into a set, or via homology, turning it into a vector space. And this perspective subsumes the traditional point cloud perspective. But you often have to do some sort of auxiliary construction. We take our points, but now we consider all the sublevel sets of, say, the distance function, and you store those as fibers of another map, which you can then interrogate by projecting onto your parameter space. But this really begs the question of what happens when you don't have this natural ordering like we had in traditional persistence of like closer distances being closer than larger distances. And so the typical kind of examples which we can now study using this sort of TDA lens is what's sort of the metric geometry of level sets of a Morse function, or more generally, what happens when we're studying maps to the plane and we have these interesting sort of cusps and folds. How can we describe that, especially because there's not like a naive inclusion from one level set to the next? And to drive this point home even further, suppose you don't care about Morse functions or maps to the plane. If you care about time varying data, you're going to run into the same phenomenon. There's not a nice mapping from something that occurs at one time to something that occurs at another time. So for example, if I have like satellites that are connected in the network, but then one sort of splits off. If I try to study this map on components, there's not a map from a single component to two components, at least not one that's continuous. And sort of the tools I'm going to provide for you provide one way of studying this instead. And so the answer, which I'm trying to kind of evangelize here a little bit here, is that sheaves and cosheaves provide a unifying language for all of these constructions. And so you can think of sort of merge trees, which track clusters in terms of cosheaves on R with a certain topology. These are like where down sets are open sets. Or you can just use Reeb graphs, and those correspond to ordinary cosheaves on the Euclidean topology. But all these other constructions kind of fit into this framework. And again, these are tools which have been developed since the 1940s. So there's a huge toolbox of ideas that you can draw upon. And they also provide kind of nice analytical models that you can sketch on a napkin. But at the end of the day, you can actually compute these things using what are called cellular sheaves and cosheaves. So I'm actually going to start with this definition and then move my way to the more general definition. So the concept of a cellular sheaf has a really rich history, but I'd like to credit Robert McPherson, who's a professor at the Institute for Advanced Study, for really identifying and solidifying this idea. And it's very elegant. So imagine you have a cell complex. You could think of just a triangulated space. A cellular sheaf is equivalent to just specifying for every cell in that cellulation or simplex in that triangulation, some sort of object. You could think of that as a set or a vector space, whatever you want to do. And whenever you have a pair of incident cells, and I want to say that two cells are incident if one is contained in the closure of the other, and I'll write that as a less than or equal to, I need to specify a morphism. So how does, let's say, the homology vector space map from one to the other, or how does the set of components map from one to the other? And there are usual properties you want to assume, such as if I have a trio of cells, then the composition of those two maps needs to be the same as if I just went from the lowest cell to the highest cell. And all that can be packaged in a very slick definition, which just says, whenever I have a cell complex, I have a poset of the cells, which record these face relations. And a cellular sheaf is just a functor from that poset. And we can dualize and get the sort of dual notion of a cosheaf as well. All right, so I want to compare this with the traditional definition of sheaves and cosheaves, which we can kind of think of as continuous objects. So we have some topological space, and that means we have open sets. And now we're going to assign to open sets some sort of data object. And whenever I have an inclusion, a pre-cosheaf is going to map covariantly. So it's going to go from smaller open sets to bigger open sets, which is, the natural direction if you like thinking of homology, for example. Now, the requirement to actually be a cosheaf is that if I want to understand this object on, let's say, a big open set, well, I can first take a cover by smaller open sets and then sort of glue together the data assigned to those smaller open sets, and I can get back this object on the bigger data set. Now, if you'll notice, there was no kind of gluing axiom in this earlier definition of a cellular sheaf. That's because we just assign data to cells, and the union of cells aren't necessarily a cell, it's just a union. So the reason why you can think of this object here, the cellular object, as a sheaf or a cosheaf, is that you can force this sheaf axiom or gluing axiom to hold when you consider a union by just defining the value to be the limit or co-limit. All right, but it's best to understand this through examples. So let's get into those. So of course, a standard construction and TDA and computational geometry is this notion of the Reeb graph. In general, if you have a map of spaces, you can always take open sets in the codomain X, look at the inverse image, and then apply pi 0. And because again, pi 0 is functorial, you have ways of connecting things that happen over smaller windows or parameter values to ones over bigger ones. So if I look at this purple open set, look at its inverse image, I get two components, which corresponds to kind of two circles here. And if I have this larger yellow or blue open set, there's natural inclusions and then induced maps. And if you just think algebraically, this is what's happening on the functor level. There's a map from this 2-element set to this 1-element set. And that actually very much looks kind of like a face relation for the Reeb graph. And in fact, you can recover that information completely from this Reeb cosheaf. The other object I'm going to refer to today is this notion of the Leray sheaf, or its sort of dual cousin, where you use homology, the Leray cosheaf. Now, in general, homology in higher degrees, so meaning degree 1, degree 2, and so on, does not form a sheaf. You have to apply some process known as sheafification. But we can kind of obscure that subtlety by just working again with small open sets and then forcing the sheaf axiom to hold on larger open sets. And getting at my earlier question, how do we connect the fibers when there's not a naive inclusion? So there's definitely no inclusion from, let's say, this wedge of circles into this pair of disjoint circles, because that would involve sending this point here to two different points. There is a way of connecting these fibers by using open sets. And the kind of general phenomenon is that if I have like a critical value or some notion of a critical value, and I look at some neighborhood that contains that, then I get, in this case, a sort of pair of pants, which actually deformation retracts onto the critical fiber, so the red pair of open sets. And so the way that sheaf theory says we can connect the fibers is, if I want to take another value here, t, look at the homology of its level set, then I can just include that inside of this kind of pair of pants, and then it will go along for the ride in this deformation retraction, which then induces maps on homology and cohomology. Now, there's a really beautiful generalization of that picture, which McPherson identified sometime in the 70s and 80s. It's sort of unknown, which is that when I have something like a Morse function, what that does is it stratifies the real line into critical values and then non-critical intervals. But I can also consider maps to the plane, which have sort of nice cusp and fold structures that will also induce a stratification of the plane. And there's a nice combinatorial gadget that allows me to organize persistent homology, or I should say homology of level sets, using something called the entrance path category. And this category is very sort of geometric. It has objects that are just points of the space. And if I have 2 points, let's say the origin and this point up in the first quadrant, I can connect them via a morphism if there's something called an entrance path that relates them. And so this is a path which travels around, and if it hits a lower dimensional stratum, in this case, the y-axis, which we think of as like a 1-dimensional stratum, versus the open quadrant here being a 2-dimensional stratum, it has to stay there, and then it can stay in that one stratum, or it can move deeper into the stratification down into this 0-dimensional stratum. So a non-entrance path is something that does this. It enters the 1-dimensional and then exits for a higher dimensional stratum. And so that's not allowed. And of course, we don't use these paths directly to form our morphisms, but rather we use some sort of equivalence relation and say that 2 entrance paths are equivalent if they're homotopic rel endpoints through entrance paths. And with this definition, suddenly there's a nice combinatorial gadget which arranges all the points in this stratification of the plane, which just looks like, again, a poset. I have a representative object for every 2 cell, which are 4 open quadrants. And then I've got representative points for my 4-1 strata. That's my positive x-axis, positive y-axis, and so on. And then 1 point for the origin. And again, these entrance paths just basically look like the opposite of the face relation poset. So the sort of folk theorem of McPherson, which has been proven in various settings by other people, and in one form by myself and my collaborator Amit Patel, is that cosheaves, which are sort of locally constant along strata, are equivalent to representations of this entrance path category. That just means a functor from the entrance path category into our data category. And this object here is suddenly very computable. In general, it just kind of looks like a quiver. So now you're looking at representations over a directed graph, or it can look like a poset. It kind of interpolates between those things. Or if you have a non-simply connected stratum, it looks like a representation of an abelian group or something like that, or even non-abelian. Now, how does this show up in TDA? Well, when we're looking at Morse functions, the entrance path category just looks like I have representative objects for non-critical intervals and then representative objects for the critical values. And there's a morphism that goes from the non-critical interval down to the critical point or critical value. And so then when I'm studying something like homology or pi0, what I'm studying is basically a collection of sets or vector spaces within maps that go down towards the critical values. And in the setting where these objects are sets, this is exactly the Reeb graph. And in the case where this is vector spaces, these look like zigzag modules, and they have barcodes. And sort of the moral I want to communicate is that, at least in the setting where we're looking at traditional zigzag persistence, there's sort of a canonical one that is adapted to exactly where the critical points are, critical values. And when you study that object, a lot of interesting dualities and things sort of emerge. But again, we can now tell you how to organize things like the Whitney cusp and fold, pick points from each of these representative strata, look at entrance paths, and then study the homology of the inverse image over each of these points. And each of these maps give you induced maps, which, sorry, in this case, decomposes actually very nicely. But this is where my story with persistence sort of stops, and I hand it over to other people. And I'll just say the kind of moral here is everyone in multi-parameter persistence is struggling with the lack of these indecomposables, but my general opinion here is that we need to kind of give up indecomposables and work with these other kinds of rank invariants or things that are analogous to that. And I steer you towards Alex McCleary and Aziz Gulen and some of Amit Patel's work. All right, so that was sort of a brief tour through traditional level set and multi-parameter persistence. I want to quickly illustrate how this perspective allows you to also generate new tools. And the reason why we need a new tool is I want to be able to discriminate data sets that kind of look like this. So here I have a data set, which I'm just going to think of as a subset of the plane. One is a disk and then a wedge of two circles. And another here is just two circles that are separated. Now, if I applied the traditional TDA pipeline by considering growing balls or the offset filtration, and then taking homology at every step of the way, I cannot tell these two data sets apart. And that to me always feels kind of weird. Like a child could tell these two data sets apart, but persistent homology in all its glory cannot. They literally give you identical barcodes. Of course, what's going on here? Well, here I have my two H1 classes on one component, and here I've got them on two components. So what I need is some sort of object that tracks how homology evolves over components. And in this setting, I'm going to sort of think of my merge trees, which tracks pi0 of this offset filtration. I'm going to decorate it with the barcodes, and I want to do this in a sort of precise way. And the sheaf theory perspective tells you immediately what to do. So if you think of your offset filtration, you can think of that as just sublevel sets of this distance function. associated to any function, we have this notion of an epigraph. And traditional sublevel set persistence says, well, I've got a space, I'm going to put a constant sheaf on it, that's, and this, the space here being the epigraph, and then I'm going to study some sort of push forward object. And this gives me, when I push forward to the real line, barcodes, because sheaves over the real line have barcode decompositions. But instead, I could have just studied sheaves here and stopped working just over the merge tree. And so one way of defining this decorated merge tree is that I'm going to use this array sheaf construction I mentioned earlier, but now associated to this quotient map Q that goes from the epigraph to the merge tree. Of course, this just looks like a cartoon, but it's something we've actually implemented in code, studied on sort of synthetic point cloud examples, and some nice things pop out, like you get cycle localization for free once you sort of modify the persistence algorithm in an appropriate way. And we've also applied this to some actual medical data as well to help see where these sort of homology features track as we move through these images. Of course, there are some nice adversarial examples, like I showed earlier, that show up when you do sort of sliding windows embedding, but then there's a jump in amplitude. So if you just do persistence, all you're going to see is that there are two bars of roughly the same length, which indicate the period. But persistence won't see that actually there was this kind of jump, which is seen in the delay embedding by the fact that there are these two circles. And we can kind of track all that information using the merge tree with the barcode. But again, this array sheaf is sort of hard to study on its own. Instead, we kind of use tricks where if I take a point in the merge tree, I can then look at all the points that stand above it, which I think of as the principal upset. And now I'm restricting a sheaf to a line. And again, I have a barcode decomposition. So I can now think of this associated to this sort of concrete decorated merge tree, something we'll call a barcode decorated merge tree, which essentially assigns to points in my merge tree barcodes, just given by restricting the filtration along that component and its forward evolution, and then and working there. But I will say that this kind of push forward operation by just looking at barcodes as they lie on the merge tree fails to see certain information. So if I take my two leaf nodes here, and I've got this kind of family of vector spaces indicated in yellow and orange, if I sit at V and I stare, well, what vector spaces do I see? I get this kind of barcode picture. And then if I sit at W, I also get this kind of barcode picture. But I would see the same thing if I had this decorated merge tree, where I've got two completely unrelated families of vector spaces in yellow and orange. So this just proves that this process of taking the array sheaves and then considering this sort of barcode transform is not injective as well. And so if you read our paper on decorated merge trees, we sort of give actually three flavors, two of which are equivalent to the array sheaf perspective. One uses this sort of new category called pvect, but then in practice we use this kind of simplification, which is also very nice because it allows us to kind of register data sets by aligning them in barcode space. And again, there's code for doing all this on Tom Needham's GitHub. All right, so I want to just sort of plug that what I've shown you in just this past section is just an example of a sheaf over a graph, and already we can do better jobs of discriminating certain data sets. But you know, the machine learning community is just starting to like catch on to this sort of fad, and there's this really nice paper by Christian Bodnar and Francesco Di Giovanni, and also the eminent Michael Bronstein, who's a very sort of high-level professor at Oxford, where they actually adapt some ideas of Rob Grice and Jacob Hansen in terms of studying Laplacians associated with cellular sheaves. And they're able to prove some really cool results about overcoming some problems in neural nets, all just by using cellular sheaves on graphs. And so there's a nice blog post about this if you're curious. Okay, so in the next sort of 10 to 15 minutes of my talk, I want to zoom out and take stock of families of data sets, families of topological summaries, and tell you how sheaf theory kind of organizes our thinking there. And the perspective is essentially the following. Whether you're studying point clouds, which are just sort of subsets of RD, or functions, which you can think of as some function space, there's always a sort of topology on our space of data sets. And this process of summarizing our data using something like a barcode itself can be viewed as a map. And so we have the picture that we already studied earlier. We have a space Y and a receiving space X. And so we can repeat and recurse the earlier constructions of Reeb cosheaves and Leray sheaves, but now applied to these big infinite dimensional constructions. And so I want to tell you some interesting results about what happens when I take even just the Reeb cosheaf of the space over the space of barcodes, where I'm looking at, say, merge trees or Reeb graphs, for example. And just to leave you all with something to think about when you go home, here's an open problem, although there was some solid progress made by my former PhD student, Jordan Deshay, which is, if I fix a certain zigzag barcode that looks like this, I've got one closed bar and then two half-open bars, I can tell you there are 4 different non-isomorphic Reeb graphs that all produce the same barcode. So this tells you that the ramification number of Reeb graphs over this barcode is 4. The general problem is, if I give you the barcode, tell me that number. That is an open problem. It's something we do not know how to do. We can bound some of these guys, but Henry will recognize this top guy up here. It's the source of so much trouble. Like PhD theses are written based on this one Reeb graph. But either way, we can talk more about that offline. Let me show you a situation where we do know the answer, and this is in the case of merge trees rather than Reeb graphs. So sometimes this is couched in the language of realization. So if I give you a barcode, I want you to produce for me a function or a space with a function that gives me that barcode. If I have just one infinite length bar, I can produce a space with a function on it very simply. It's just going to be the embedding of this interval into the real axis, which I can think of actually as a merge tree. But if I add a point, let's say now this is a finite length bar, so I represent it as a point above the diagonal, I can produce another space that realizes this barcode. And essentially what I do is I take this bar and I attach it to the spine that I already laid down. And this makes sense. Like, barcodes don't have adjacency information, but graphs, trees do. So I just need to tell you some adjacency data when our 2 bars sort of adjacent. So let me add another point. Here, I now actually have 2 different merge trees, which give me the same barcode. So this is one, and here's the other. And you'll see that all I did is I changed which branch I attached to. And these actually are non-isomorphic merge trees. Now, what happens if I change the configuration of my persistence diagram? So I move this point a little bit out of the way. So I now move from here to now this point. So again, I can produce one realization that just takes this now slightly longer bar because I've made it born earlier, but I've kept its death time constant. So now it's just a little bit longer on the back end. But you could say, well, why can't I attach it here? So the question is this a realization? And the answer is no. again, by a somewhat sort of apocryphal rule known as the Elder Rule, which essentially says that I can determine the barcode via a branch decomposition of this merge tree. And if I followed that rule, what would happen is that I have a class that's born here. Okay, so that corresponds to this bar. But then as I move up and I'm about to merge with the class that was born earlier or later, the Elder Rule says that the eldest must survive and the young must die. And so the death time actually isn't here, but up here. So if I tried to kind of attach to a different one, I actually map to a different barcode. So the general theorem, and this is something I wrote down in 2017 and then was later rediscovered by Adelie Guerin, Catherine Hess, and Lita Canary, is that if I have a barcode with one infinite bar and then a handful of finite length bars, all that are born later, then I can associate to every bar in my barcode a number, which I call mu bij. And this just tracks the number of other intervals in my barcode that were born earlier, so its index is earlier if I label by birth times, that die later. All right, so alternatively, mu bij is the number of intervals in my barcode that contains a given interval. Or in the language of persistence diagrams, it's the number of points up and to the left. Now, if I take the product of these numbers over all my finite bars, I get a number, and that turns out to be the tree realization number, which I'll just call the realization number for short. And so in the previous example, we said this was 2, and then in another one, it was only 1. Now, the interpretation of this number is that you want to imagine there's this whole space of merge trees mapping down to the space of barcodes, and the number of sheets that lie above certain configurations of barcodes changes. So it's kind of like a book mapping down to a plane. And this formula RB tells you how many pages are in this book that map down to this plane here. I want to give you another interpretation of this, which I think is quite nice. And this is an observation completely due to Adelie Guerin, Catherine Hess, and Lita Canary. So they were very clever, and they observed that persistence diagrams and general configurations you can actually think of as elements of the symmetric group. How does that work? Well, if I label my points by increasing birth time, I can then ask, in what order did they die? And that defines a bijection. So here I've got born first dies first, born second dies second, born third dies third. So this is the identity permutation. But these other points, here I've got born third dies second, so I can represent that as the elementary transposition 2, 3. And associated to any element of the symmetric group is something called a left inversion vector, which essentially counts the number of upsets in the natural order of things. And if I take this left inversion vector, which uniquely coordinatizes elements of the symmetric group, and I add 1 to every entry, and then I take the product of those entries, I then get my realization number. So I can now think of this number as actually a function on the symmetric group, which I think is pretty cool. And of course, there are other nice properties, like if you put the Bruhat order on the symmetric group, this number is order increasing. And of course, if you study the Cayley graph, this is sort of an interesting function on the Cayley graph. But I kind of want to skip ahead a little bit here. But if you go back to that kind of book picture, I want to use this number to count the total number of pages, which are really the orthents in the space of merge trees. And so one way of reason for doing this is there's this famous work by Balera, Holmes, and Voigtman that counts the different split topologies, which really are the different orthents in phylogenetic tree space. And I want a similar number for merge tree space. So one nice observation is that both these strata of barcode space, which are indexed by elements of the symmetric group, and the corresponding strata that sit above them in merge tree space are convex. So as long as I don't change birth and death order in my merge trees, I can kind of drag endpoints as I like. And so this allows me to kind of put merge trees in standard form, where I have leaf nodes at prescribed heights 0, 1, 2, 3, and then I have internal nodes at prescribed heights n+1, n+2, n+3, and so on. And so what are typical merge trees? Well, if I have a death value at n+1, I need to pick two components which were born at respective times to die at that value. So, and then as I move up, I got to pick another two and another two until I have exhausted everything and the space is connected. So this is one standard merge tree. Here's another. And if I do it again, here's another. And if I had more time, I'd let you puzzle out the pattern yourself. But what you should see is that at each stage of my death values, I have first n+1 different leaf nodes. I pick two of them to merge. And then now I have one fewer equivalence class connected components. I pick two from there to merge. And I just take the product over all these operations and I get this really nice formula. And this formula actually shows up somewhere else. This counts the number of maximal chains in the lattice of partitions. And this is actually a result of Erdős that we ended up rediscovering. And kind of the cool thing is if you ask, well, how many orthents are there in merge tree space? There's this many. And you should compare that with the number of orthents in BHV space, which corresponds to this 2n-1 double factorial. And so just for concreteness, if you have 4 leaves, they're basically 15 different split topologies. But if you have 4 leaf nodes, which kind of correspond to 3 finite length bars in merge trees, they're actually 18, and they're organized in a much more interesting way. All right, so I'll just say that, again, merge tree space is a slightly different animal than phylogenetic tree space, and there's a lot of interesting combinatorics and statistics that needs to be done here. But I want to get to my last story here in my last sort of 5 minutes, if I may. So earlier we talked about this pipeline of data to these sort of intermediary topological summary objects. I want to provide a different perspective on the space of data sets that takes advantage of this really neat construction called the persistent homology transform. And so this was something that was really investigated and popularized by Kate Turner and her co-authors Cheyenne Mukherjee and Doug Boyer, both at Duke at the time. And the idea here is that our data sets are going to be subsets of RD. And so here I'm going to think of the letter M as a instance of a data set, and I'm going to study it by picking a direction and scanning in that direction and sweeping and taking persistent homology. So if I look in this direction, I'll see only one component born, which is this side of M, and then nothing else happens. But if I look up in the vertical direction, I'll see that I've got these 2 legs that are born, which kind of corresponds to these 2 points here. And then another feature is born here, which I think corresponds to this guy. And then there's a death event where some of these merge and then some of these persist forever. And so one of the reasons why we like the PHT is that if you look in all directions and you take persistent homology, it completely determines the shape. So this was an injectivity result first proved by Kate Turner and Cheyenne and Doug Boyer, 2014, in the setting of PL embedded simplicial complexes in R3. So the statement goes that if I have 2 of these in R3 and their PHTs are the same, then the subsets actually are the same. And then a few years later, I, in collaboration with Kate and Cheyenne, and then separately, Rob Greist and Rachel Levanger and Hui Mai used some work of Shapira's to show that the result holds for all dimensions and for any sufficiently nice subset. So semi-algebraic sets, the same result holds true. Now one perspective which is sort of mentioned in the latter paper with Kate and Cheyenne is that, again, you can think of the PHT as a sheaf. And the way to do that is you again build this sort of auxiliary space, which I call ZM, which records all sublevel sets in all directions. And then now you'll see that this space naturally has 2 factors in the sphere, which is our direction space, and then R, which is our filtration parameter. So I can just project ZM down to SD-1. And if I study the Leray sheaves of this map, I get the persistent homology transform. And And if I want to get the usual picture of associating to a direction of persistence diagram, all I do is I'm just restricting that sheaf to my specified direction and cross with R. Now, a few years later, Shreya Arya, who's a really brilliant grad student at Duke, working with Cheyenne, made the observation that if I have two subsets, A included inside of M, then there's a natural inclusion of these auxiliary spaces, ZA and ZM. And consequently, if I just restrict cohomology of the sublevel set inside of M to the cohomology of the sublevel set inside of A, then I get a map of sheaves. And so the first observation was that this actually defines a pre-sheaf on the post set of constructible subsets and their inclusion. Of course, because we're using cohomology, things become order reversing. But now the data object that we're assigning to it is this sheaf that keeps track of cohomology in all degrees, which we think of as the derived PHT. And so this might be a little hard to visualize, but here, if you take this kind of picture of in R2, I can think of the sphere across R as sort of a cylinder, because the sphere is just S1. And then I can kind of apply this sort of stereographic projection where I put one into the cylinder, the minus infinity towards the origin, and then I get higher filtration values when I move out. And so the story basically goes, if I have this like green subset and I pick a direction that looks in this way and I start filtering, then I see that these two little nodes come into existence at time 0. That's why I have a K2 here. And then by the time that my filtration parameter reaches 1, they will end up connecting. And so then the rank of homology drops. And so I can obtain the barcode in that direction just by restricting this sheaf along this axis. And of course, similar things true if I go the other direction. And if I look at the 2 points, the blue and the purple point sitting inside, here's what these kind of PHT sheaves look like on this sort of cylinder, but projected onto R2. And the observation is that I should be able to use these 3 objects to recover the PHT of the entire circle. And we did some calculations and we saw that this all seemed to be true. And then we also proved the following result, which made us think that actually this PHT, which I can think of as a pre-sheaf on the space of all possible nice subsets, might actually be something like a sheaf. And so the first setting we considered is if M is a polyhedron, so it's sort of covered by convex shapes. Well, any given convex shape only is going to have homology in degree 0. But if I take my shape M and I kind of cover it by its top dimensional facets, and I look at these PHT sheaves, then I can organize these restriction maps into something that looks like essentially a nerve lemma for the PHT. And so the result we prove is that if I want to know persistent homology of a polyhedron M in degree n, that's a sheaf. That's equivalent to the nth cohomology of this complex of sheaves. All right, I see I'm running out of time. Let me just give you the punchline here is that in general, the persistent homology transforms into something that we call a homotopy sheaf, which essentially requires that we look at higher depth intersections. And instead of using an ordinary limit, we use something called a homotopy limit. And we're really excited about this result because all these previous constructions of shape space, whether it's Kendall or Grenander, make the assumption that all the spaces involved are diffeomorphic. Here we can actually consider spaces with different topology, but they're all sort of faithfully represented using this PHT, which again, kind of feels like something that sort of fibers over the space of shapes in an interesting way. All right, so here are a bunch of references. If you go in the links, I welcome you to read these. And I thank you all for your attention, and I apologize for going over time.
Thank you. So maybe let's first unmute ourselves and thank Justin with a little applause. Okay, so before we start with questions, there was one question in the chat window that I'm going to ask now before I let others continue. So are there folks who are looking at to applications which use generalizations of these tools to cellular slash simplicial sheaves, like where D is chain complexes of vector spaces? So that was asked a little bit earlier, but I said I would ask it at the end.
Yeah. So the short answer is no. But if you think of this object here, this kind of derived PHT sheaf, you can really think of that as a sheaf of chain complexes, and so that ends up being, if you want to take kind of a discrete approximation of this object, I think you would end up getting an object very much like that. But in terms of real applications, I haven't seen much in the way there, but the theory does go through. But thank you for the question.
Thank you. As soon as you had that slide, I realized I should have held my question.
No. It's great. But yes, you're barking up the right tree.
More questions. Yeah, so unmute yourself if you want to ask.
So I have a question, but my camera is failing me. So I apologize that I'm all black here. Oh, here it is. Okay, not that I'm interesting to look at. Actually, this slide is a good slide to ask this question. So I'm working with abstract simplicial complexes, and you're here in the geometric setting. Have you looked at what happened when you just do the combinatorial information of simplicial complexes?
Right. So meaning, yes.
Meaning you don't necessarily have an embedding, right? Right. You may just have the abstract simplicial complex, and you have not decided yet on some way to put in the space. It may be an immersion. It may be something really unpleasant. But you know, you may have a geometrization that actually is an embedding. But you know, you can just take an abstract simplicial complex and have inclusions out of that combinatorial data. So we can do persistent homology in that setting. We don't actually need the metric information. So I'm kind of wondering if you had thought about what the metric information does and how much this sort of works in the more abstract setting.
Yeah. So I should say I have. I mean, if I go back to the kind of beginning picture, so one setting is, you know, if you have just a cover of a space, right? Then we know that you can always take the nerve of this covering. And so if I take cohomology of those cover elements, either them as a single cover element or looking at the intersections, then you end up getting like a cellular sheaf over the nerve. And so first of all, like, you know, our usual things like the like essentially the good cover condition guarantees that there's not really any interesting sheaf cohomology when you then run the computation. But a lot of we still know that you can recover the cohomology of the space from a cover by using this kind of Vietoris spectral sequence argument. And so I think all that is like beautifully expressed in the language of cellular sheaf theory. It just maybe isn't quite as exciting because you know, old school algebraic topologists will be like, oh yeah, I'm familiar with that, but you're just calling it a different thing. But that said, like, I still think there's a lot of value to just considering these sort of systems of subsets and then looking at the induced inclusions just combinatorially and then study things like, well, what homological information can we recover if we just look at certain parts of that system and see how things persist across inclusions. Yeah, I still think that is very interesting. Just hasn't had like a killer app, which makes people really convinced that this is the right thing to do.
Yeah, so it's not a killer app, but what I do is I do synthetic stuff. So I build spaces. And so it's nice to have the abstract set to then do an embedding or geometrization. And so that's part of the synthetic step. So in where I work, this is a good setting for me. But it hasn't killed anybody yet. So it's not a killer app. Thank you so much. Very, very interesting work. Thank you.
Yeah, thank you for the question. I'd be happy to chat more about what you're doing. Elkanon, I think you have your hand up.
Yep.
Yeah, so it's just kind of a meta question. So, and it applies, I think, particularly to the PhD, but maybe it's more general than that. So, one of the things that I sort of interesting in the injectivity theory, for example, for the PhD, is that there's all this beautiful structure, but somehow to prove things, you have to throw a lot of it away because it works with Euler characteristics.
Yeah.
And the Euler characteristics don't enjoy, unless I'm mistaken, don't enjoy very much structure. And I can think of some other examples where this happens. And I'm wondering if you have any insight on sort of, this really beautiful structure. Somehow it's actually hard to prove things with, and you throw things away, then you get something without the structure, and that's what's needed. And so you have a feeling like maybe these things should be provable directly with homology without having to go to Euler characteristics, or there's something combinatorial that you need to work with? Yeah, that's the kind of question.
Yeah, well, I'll mention only one example, and this is just something that I realized somewhat recently, where homology actually does a better job than Euler characteristic, and it's with regards to stability properties when filtering a space and given directions. So normally, if you pick a direction, you look at the Euler curve, you get a function out. And if you pick a nearby direction, you look at its Euler curve, and you try to compare those curves using L infinity distance, so function distance, then you're going to get a discontinuity. And so that kind of L infinity difference distance actually is not a stability property that the PHT, or I should say the ECT, enjoys. But actually, if you use homology, I believe the L infinity distance is still stable. So there's like this one parameter value in which like homology is slightly more stable than Euler characteristic. But to your broader question, I should say that this theorem that's on the slide right here was actually motivated by exactly that question of like, why do we need Euler characteristic? Because actually intuitively, if I have like, say, a submanifold, I should be able to determine that submanifold of RD just by looking at the first birth time, because that will kind of like tell me where there's a point in my set. And if I move this direction around, I should be able to apply something like an inverse function theorem that starts covering my set. And so really, like, not only should Euler characteristics satisfy, but actually like homology in degree 0 should satisfy, and not even just all homology, just literally like the first birth value. So I claim that there should be an injectivity result that just looks at this like first entrance point in the filtration when you look in all directions. But again, you need some extra assumptions, I think, on the space. But you're absolutely right. Like, there is something that's kind of unsatisfying here, that like everything factors through functions. But I still believe that, I mean, one thing which is true, again, when you use homology but not Euler characteristic, is I don't think you get the same kind of reconstruction result. Maybe you do, and of course, if anyone on this call has thought about how to glue together Euler characteristics, it's you, Elkanon. So my challenge to you is, prove a gluing theorem for the ECT instead.
I see you've answered the question with a homework assignment, but that's it. That's an interesting answer. Thank you.
Yeah.
Okay, do we have any further questions for Justin?
I think Matt Pekenbrock has a question in the chat. Matt, do you want to say it aloud, or should I just read it?
Yeah, sure. There's some background.
Okay.
But you just briefly.
Okay, so Matt asks, the injectivity of the PHT enables a distance between shapes, which is not diffeomorphic, and also mentioned two other distances, which assume the shapes being compared are diffeomorphic. One was the Kendall shape space. What was the other one? Right. So, there's this. So Kendall basically just takes a shape, represents it as essentially a point cloud by looking at landmarks, and then measures distances between matrices in terms of how much do you need to align or rotate one matrix to get to the other. Grenander is and really kind of augured by earlier work by Peter Mikor, who's a differential geometer. His distance essentially says what's the energy of a diffeomorphism of the ambient space that will take one subset to the other. And so it's very much like an optimal control problem. Like, how do I flow this kind of gnarled heel bone to this other gnarled heel bone, and measuring the energy of that diffeomorphism is the distance. But again, hopefully that answered your question.
Yeah, so I hadn't heard of that. Do you know, is it computable? Probably not.
Yeah, so again, as much as we love analysis and differential geometry, it's there are some algorithms. So I know some people have taken like plane curves and then actually like solved like what is the how do you flow one plane curve to another plane curve and measure the energy there. But there are some other subtleties as well, which is that actually some of these distances kind of break down because of like reparameterization effects. And that's like a whole nother interesting sort of technical subtlety. But there's some literature I can point you towards.
Thank you.
Yeah, and thank you for the question.
Okay, so Justin, thanks so much again for the wonderful talk. So I'm going to stop the recording here, and for the last, like if you have any further questions, they can be offline.